Hello, good evening, everyone. My name is Samardeep Singh, and I'm from Manipal University, Jaipur, pursuing BTech in Information Technology. Our paper is about coral reef detection using deep learning, which we have added attenuation and backscatter for the various deep water environments. And we have also used various deep learning models to detect the coral reefs. So as we know, the coral reefs are vital to the marine ecosystems, providing habitat and sustenance for a diverse area of marine life. By integrating sophisticated pre-processing methods to correct for attenuation and backscatter, we aim to improve the clarity and accuracy of underwater images. So the data was collected by CSIR and IO from the Lakshadweep and Grand Islet images, and the rest of the data was collected from datasets like Elliot and Coronet. Labeling was done manually and performed by tools like Label IMG. Each image was annotated with bounding boxes to create a labeled dataset for training. So the problems in coral reef detection are that underwater vehicles such as ROVs and robots face significant difficulties in accurately estimating and detecting corals while in motion. This impacts the data quality and hinders effective monitoring and conservation efforts. The second problem is that underwater environments vary greatly in different water bodies and regions. Factors such as water clarity and turbidity and spectral response of the underwater and other water properties contribute to significant differences in image quality and appearance. So what is attenuation and backscatter? Attenuation refers to the reduction in light intensity as it travels through water. This effect is caused by absorption and scattering. As you can see, the left side indicates the non-attenuated image and the right side indicates the attenuated image. As you move further, or you can say as the range increases, the image becomes darker and less clear to see. Backscatter occurs when light reflects off particles and suspended in water and returns to the camera. The effect creates a haze or fog or a blurry effect that can obscure objects in underwater images. So the first paper we referred to was a see-through paper, which presents a comprehensive approach to improving underwater image clarity by addressing light attenuation and backscatter. The paper emphasizes the effectiveness of their method in enhancing underwater imagery for better visual quality and more reliable analysis. So the main underwater image formation equation is IC equal to DC plus BC, where C represents the color channel, which is R, G, and B. And DC is the direct signal, which contains the information about the attenuated scene, and BC is the backscatter. As you can see in the graph, the intensity decreases for a while, and as the range increases, it becomes a constant. And the backscatter, as you can see, increases for a while and then becomes a constant. And the attenuation, as discussed in the image before, as farther we move away, the image becomes darker and less clear. So it decreases for a while and then comes to zero. The equation expanded looks like this. IC is the original image intensity. JC is the true scene radiance without the added attenuation and backscatter. The beta CDVD is the attenuation coefficient, which depends on various factors such as distance, reflectance, spectral response of the camera, ambient light, and other water properties. BC infinity is the backscatter component. It represents the intensity of light scattered back to the camera. And the BC, beta CB and VB represents the backscatter attenuation coefficient, which also depends on various factors such as the attenuation component, and the term describes how much of the backscattered light is attenuated before it reaches the camera. Z is the depth, or you can say the distance between the camera and the object in the scene. The second paper we referred to was a deep sea color paper, which introduces an advanced model for underwater image formation. The deep sea color paper mainly gives us the values of the image formation equation in the previous paper. The attenuation component becomes IC equal to JC into AC plus BC, where AC equal to minus E raised power A into Z, which is the depth. And the backscatter component becomes BC I comma J equal to BC infinity 1 minus the attenuation component. So the BC infinity component becomes 0.01, as I as I told in the graph earlier, that backscatter increases for a while and then becomes a constant. So the constant is taken as 0.01. Then we applied this function to every channel differently, channel representing red, green, and blue. As red light absorbs faster, so the red channel experiences greater attenuation than the green channel and the less in the blue channel. Then in the backscatter component, which changes is that blue light scatters more, leading to higher backscatter in the blue channel than in the green and the least in the red channel. So this function was computed in a code and applied to the data which we had. As you can see, the left side presents the image before adding attenuation and backscatter, and the right side shows the two images after applying attenuation and backscatter. You can see the difference in color and the blurriness and the effect of attenuation and backscatter. Now, this is a normal image of a car and trees before and after applying attenuation and backscatter. So after the dataset was ready, we performed the deep learning model, which we use in this is YOLO, you only look once, is a state-of-the-art object detection model that stands out due to its high speed and accuracy. It uses single pass detection. YOLO processes the entire image in one go and predicts multiple bounding boxes and class probabilities simultaneously. It uses a grid-based prediction. YOLO divides the image into grids and predicts bounding boxes and class scores for each grid cell, enhancing detection across different regions. I'll discuss some about the YOLO V8 backbone. The first layer is the input image layer where the images go as input. The second layer is the backbone, which has various features. The backbone which YOLO uses is the CSP darknet backbone. It has cross-stage partial connections. This approach splits the feature map of the base layer into two parts. One part is passed through several CNN or convolutional layers, and the second part bypasses the bottleneck layers. The difference in these layers are that the batch normalization function and the activation function of these layers are different. So the features generated are different, which helps the model to be robust. Third feature is that the stage-wise feature extraction, CSP darknet is organized into stages, and with each stage compromising several CSP blocks and convolutional layers. The third layer is the FPN layer, the feature pyramid network. It has two pathways, top-down and bottom-down. The top-down pathway aggregates scores. It extracts high-level features from deeper layers, and the bottom-down pathway enhances those features by integrating fine spatial details from the earlier layers. The next layer is the SPP layer, which is the spatial pyramid pooling. It pools feature at multiple scales. That is, every feature is different at every different scale image. Like every feature will be different in a 1:1 scale image, and every feature will be different in a 64:64 scale image. So the last layer is the detection head, where the final object detection takes place. It processes the aggregate feature maps from the FPN and SPP layers to generate bounding box predictions and class probabilities. The results as follows. The first model we used was the YOLO V5 model, which gave an accuracy of 90%. The second model was the YOLO V8 model, which gave an accuracy of 83%. And the YOLO V9 model gave an accuracy of 80%. The best accuracy was given by the YOLO V10 model, which was 99.4%. As you can see, the precision confidence curve, it's nearly perfect. Now I'll show you an example of the predicted bounding box images which the model was showing. These are the actual labels, the true labels. And the next image I will show you will show the predicted labels from the model. So as you can see, there are nearly same and there is no difference between them. So in conclusion, the underwater images with the simulated attenuation and backscatter leads to improved accuracy in correlative detection. And this approach demonstrates the value of data augmentation for better model performance in diverse underwater environments. Models trained on the enhanced dataset like YOLO V8, V5, V9, and V10 showed significant gains in accuracy, precision, and recall compared to the baseline. Thank you.